Welcome to this training module, Enthalpy and HVAC Performance. In this training module, we're going to learn what is sensible and latent heat and how to calculate the sensible, latent, and total heat using some simple formulas that are easy to find either on an app or to commit to memory. We'll also use these very simple formulas in the field to diagnose problems and verify that an HVAC system is performing correctly and to specification. We'll even cover some sample service calls to demonstrate how to use this training in the field. So the first thing we need to talk about is what is heat? Well, the definition for air conditioning is a process of removing heat from a desired space and rejecting it where it is non-objectionable. So let's think about that for a minute. When we're air conditioning a building, we're absorbing the heat from that building through the evaporator and the blower and the duct system. And then we are carrying that heat over to the condensing unit where we are rejecting it. And that's the hot air that you feel coming off a condensing unit in air conditioning mode. But heat is a form of energy. And it's really important to understand the difference between heat and temperature. Temperature is different from heat. Temperature measures the intensity of heat. So for example, if you lit a match, that match would be very hot. But would that match be able to boil a pot of water on the stove? Well, no. And that represents the difference between heat and the intensity of heat. While that match was very hot, it doesn't have a lot of heat content to it. It can't do a lot of work. So again, heat is a form of energy. Temperature is different from heat. It measures the intensity of heat. And there are two forms of heat that we talk about when it comes to comfort cooling, and that's sensible heat and latent heat. Sensible heat can be measured very easily by a simple thermometer. That's something that you're going to carry on your service truck pretty much from day one. And when we're measuring sensible heat, it's important that we understand that we're measuring what's called dry bulb temperature. The reason why it's called dry bulb is that it does not account for any moisture or wetness in the air. So it does not factor in the heat that's present in the moisture or the humidity in the air. And the unit of measurement for sensible heat is BTU per hour. And so we're going to see that unit for measurement a lot today, BTUs per hour. So the sensible heat formula is useful for calculating how much sensible heat is gained or lost. And so it's important to understand what a gain and a loss is. In a heating system, we are gaining heat, we're adding heat to the space. But when we're talking about cooling or air conditioning, we're talking about losing heat. So it would be a sensible heat loss. In order to calculate sensible heat, we need to have some information first. We need to measure temperature. And again, that temperature is dry bulb temperature. We need to be able to measure our return air temperature and our supply air dry bulb temperature. And we will also need to, as accurately as possible, measure and calculate our CFM or our airflow. There's a temperature difference that we're going to be actively interested in, and that's the difference, the split between return air temperature and supply air temperature. So in order to have the temperature difference or temperature split, we need to be able to accurately measure that return air dry bulb and the supply air dry bulb temperature. So before we look at this sensible heat formula, we need to be able to understand what the symbols in that formula will mean. And it's not hard. Don't get confused or intimidated by seeing symbols that you don't recognize. The first symbol that we're going to see is Q, and that is a scientific symbol for heat energy that's used in physics. QS is what we're going to call today the sensible heat energy. So that is the sensible heat in BTUs per pound that we're calculating using the sensible heat formula. So here's our formula. Our sensible heat equals our temperature difference times our CFMs times a constant of 1.08. And that constant, 1.08, will appear every time. We don't really need to go into how we calculate or how we know that 1.08 is the case. For service technicians, that's just a number that we need to remember and plug into that formula every time. So let's use the sensible heat formula in a heating example. We're working on a gas furnace that is running a 70-degree return air temperature. Again, that's dry bulb temperature. When we measure our supply air temperature, it's 130 degrees. So that's a typical gas furnace that we're going to see in the field over and over again. And when we measure our CFMs, we come up to 1200 CFMs. So what is the sensible heat output? How much sensible heat is that gas furnace putting out? Well, let's plug it into the sensible heat formula. We're going to take our 60, which is the temperature difference between 70 and 130. So that's our temperature split, is 60, times 1200 CFMs, times that constant of 1.08. We'll plug that into the calculator, and we arrive at 77,760 BTUs per hour. That's how much heat that gas furnace, as it's running right now, is putting out. So when we take this sensible heat formula and we compare it against the manufacturer's specifications of that furnace, is that furnace operating correctly? Well, let's say that the manufacturer's specs say that it is a 100,000 BTU input furnace and that it is an 80% efficient furnace. Is it running correctly? Well, it's very easy to calculate what the performance or the output should be on that furnace. We take our input, 100,000, times our percent efficiency, which is 80% or 0.8, and we arrive at 80,000 BTUs. Now, from our sensible heat formula, we said that the furnace is actually performing at 77,760. So it's very close, within 3%. Why may it be a little bit off? Why aren't we calculating exactly 80,000 BTUs per hour? Well, there are a few factors that are in play. For one thing, the utility company may have altered the fuel mixture a little bit, so that could be in play. The other factor is elevation. If we're really close to sea level or we're at a higher elevation, that can affect not only the heat content of natural gas, but also the airflow. And airflow measurement is very hard to be exact in the field as a technician. The instrumentation that we carry on the field to measure airflow is good, but it's not laboratory quality. So we could be a little bit off. So if you're within 5% of what your specified number is, that is acceptable and there's no reason to be alarmed. In this case, we're within 3%. So we're going to move on to our next check. Now let's apply the sensible heat formula to a cooling system. So we have an air conditioning unit that's running a 75-degree return air temperature and a 55-degree supply air temperature. And when we measure airflow, we arrive at 1200 CFM. So again, using our sensible heat formula, we plug those numbers in. We have a 20-degree delta T, or temperature difference. That's 75 minus 55 is 20. Times 1200 CFMs times 1.08. We arrive at 25,920 BTUs per hour. Or when we divide by 12,000, we arrive to 2.16 tons. Which that's really important information, but sensible heat only tells us part of the story in cooling. Why is that the case? Well, when we are cooling, we're removing not only temperature or dry bulb heat, but we're also removing some moisture. And so sensible heat only tells us one part of the story. The moisture heat that's being removed has to be calculated using the latent heat formula, which is what we'll discuss next. Latent heat, from its root word latent, means hidden. And it's called hidden heat because it can't be measured easily. It can't be measured by a simple dry bulb thermometer the way you can measure sensible heat. It's the heat that's contained in the moisture of the air, which again is very difficult to measure, but it is possible. The more humid the air is, then the more latent heat exists. And latent heat is also calculated in BTUs per hour. Okay, let's pause for a second and talk about measuring moisture. Moisture in the air has to be quantified in order to calculate the latent heat removal. So it's maybe hard to think about there being moisture in the air. but if you've ever been on a humid day looking outside and you kind of see a haze in the air, maybe it's a foggy day, that's a really good example of moisture in the air. But even if you can't see the moisture in the air, it's still there, especially in humid climates like the southeast United States. The unit for measurement of the moisture, the actual moisture in the air, is grains of water per pound of dry air, or grains per pound. So what is a grain? Well, grain is a very small unit of measurement for moisture. In fact, there are 7,000 grains in 1 pound of water. That gives you any reference point. So we're talking about very small amounts of water, but they have a huge effect on the heat content of air. This is also called in psychrometric specific humidity. Now that differs from relative humidity. Specific humidity measures the actual moisture in the air, the actual number of grains of moisture in the air without the influence of air temperature. But relative humidity compares the moisture in the air as a percentage of how much moisture the air could hold. So it's important to understand the difference between specific humidity and relative humidity. Think of it like a sponge. If you have a dry sponge and you pour some water on it, let's say you pour a cup of water on a very large sponge. The cup of water is your specific humidity. When you pour that into the sponge, that sponge is either 10%, 50%, or 100% filled with water. That's your relative humidity, how much water that sponge can hold compared to how much water is actually inside of it. So it's a percentage. So specific humidity, again, is the amount of water in the air, or the grains of moisture in the air, and relative humidity is the percentage of moisture in the air compared to how much moisture the air could hold. With that knowledge, we can talk about the latent heat formula. It's used to calculate how much heat in the moisture of the air is being removed by an air conditioning system. In order to calculate latent heat, we're going to need the following information: the grains of moisture in the air in our return side, and our grains of moisture on our supply side. So how many grains are we starting out with before our air passes through the evaporator coil, and how many grains are present after it leaves the evaporator coil? And just like the sensible heat formula, we'll need to know how many CFMs of air we're moving. Now, when we see GD, that's grains difference between supply and return. So if you remember the sensible heat formula, we were looking for temperature difference between supply and return, or our temperature split. Now with latent heat formula, we're looking for our grains of moisture difference between supply and return. So it's a similar concept. Instead of temperature, dry bulb temperature this time, we're looking at grains of moisture difference between supply and return. So here's our formula. We again see the letter Q, which means our heat. And that little L next to it means that we're talking about latent heat. So latent heat equals grains difference, grains of moisture difference, times our CFMs, times a 0.68 constant. So just like the sensible heat formula had a constant that appears every time, so does the latent heat. Only this time it's 0.68. So how do we calculate what our grains of moisture difference is? Well, we have to go to the psychrometric chart or use a psychrometric app. Well, it's a little easier to visualize what we're doing on the psychrometric chart, and a lot of technicians get intimidated by this chart. There's a lot of lines are going in a lot of different directions, but the psychrometric chart is useful because we can plot points on the chart that represent the properties of air. So it's not practically possible to measure grains of moisture in the air using instrumentation, so we're going to plot it on the psychrometric chart. If we know our dry bulb and wet bulb temperature, then we can plot a point on the chart and get our grains of moisture from this chart. In order to plot a point on the psychrometric chart, we need to be able to measure the dry bulb and the wet bulb temperature of the air. An instrument that can do that is called a hygrometer. It can measure both dry bulb and wet bulb temperature. You see two examples of hygrometers that technicians use in the field. One's made by Fieldpiece, the other one is made by Testo. There are others, they're very accurate, they're affordable, and it's important to have two of them. That way you can take both your supply and your return air readings simultaneously. So now that we have a set of hygrometers, we can now use these and plot these points on a psychrometric chart, and then we can understand what our grains of difference is between our return and our supply. So the same air conditioning unit that we've started talking about is running 75-degree dry bulb, 63 degrees wet bulb temperature. Let's go ahead and plot these points. Here's our 75-degree dry bulb return. Here's our 63-degree wet bulb. So here's our return operating point. When we carry that operating point all the way across to the right, we get to our grains of moisture, of our return, which is 65 grains. Now let's talk about our supply. Here's our supply dry bulb, 55 degrees. Our wet bulb is 50 degrees. So here's our operating point. And when we carry that all the way to the right, we arrive at 45 grains of moisture. So what's our grains difference? It's going to be 20 grains difference. The difference between 65 and 45. That's our grains difference that we're going to plug into the latent heat formula. So now let's plug these points into our latent heat formula. That air conditioning system, as we just discussed, is removing 20 grains of moisture at 1200 CFM. So what is the latent heat removed? We're going to plug these into our latent heat formula. Again, here's our formula, and here's our numbers plugged into that formula. What do we arrive at? 16,320 BTUs per hour, or 1.36 tons. So far we've discussed sensible heat and latent heat. And now we can put the two of those together to arrive at total heat. So total heat can be calculated two different ways. We can add our sensible and our latent heat, or we can use another formula called the total heat formula to measure enthalpy. So let's talk about adding sensible and latent heat together. What did our system that we just tested produce? Well, in our example, the unit removed 25,920 BTUs per hour of sensible and 16,320 BTUs of latent heat. So to calculate total heat, we just add those two numbers together, sensible plus latent, and we arrive at 42,240 BTUs per hour, or 3.52 tons. So this system is operating right around 3.5 tons. Very easy formula to plug in, just adding those two numbers together, sensible and latent. Let's pause for a moment and talk about sensible heat ratio, because this is very important when we're talking about the performance of the system. Sensible heat ratio is the percentage that sensible heat is to total heat. So in our sample unit, the air conditioning system removed a total of 42,240 BTUs. Of that, 25,920 was sensible heat. So the sensible heat ratio is calculated by sensible heat divided by total heat. Again, a very simple formula. In this case, we divide 25,920 sensible divided by 42,240 of total heat. We arrive at 0.61. What does this tell us? It tells us that 61% of the air conditioning's capacity was sensible, which tells us also that 39% must be latent. If it's not sensible, it has to be latent. There is no other alternative. Your typical residential air conditioning system sensible heat ratio is between 0.7 and 0.8. The higher the sensible heat ratio is, the quicker that system will satisfy the thermostat, because it's removing more sensible heat than latent heat. So it's taking temperature away from the house, but it won't be very good at removing humidity. So if a home is experiencing high humidity, that may mean that the AC's sensible heat ratio is too high. It's satisfying the thermostat before it can run long enough to remove humidity. So what can you do? Well, in order to lower that sensible heat ratio or make the system better at dehumidifying, you can slow the fan speed down. To raise the sensible heat ratio so that the air conditioning can reach temperature quicker, we can speed the fan up. If you recall, we said there were two ways to calculate total heat. We could add sensible and latent heat together, which is what we just talked about, or we can use the total heat formula to calculate total heat. Total heat is also called enthalpy, which is an important term to remember. The total heat formula is actually a more direct method of calculating total heat that's removed from a system. So that's the method that you'll use in the field more likely. Similar to the latent heat formula, it requires us to plot 2 points on the psychrometric chart. And then instead of calculating grains of moisture, we're actually going to be calculating and measuring and doing math to figure out what our enthalpy is. Well, what is enthalpy? Simply put, enthalpy is the total heat in the air. Enthalpy is heat. Its unit for measurement is just the same as sensible and latent heat. It's BTUs per pound of dry air. And is directly connected with wet bulb temperature. So enthalpy takes into consideration the moisture level in the air. And on the psychrometric chart, it's simply an extension of the wet bulb line. So we still have our sample air conditioning problem that we're working through. This system, as we can see here, we have plotted two operating points, our return and our supply. Again, our return was 75 dry bulb, 63 wet bulb. Our supply was 55 dry bulb and 50 wet bulb. That's how we arrive at our operating points. Now let's try to plot our enthalpy. The enthalpy is just an extension of the wet bulb line, which runs diagonal on our chart. So if we plot this out, we arrive at 28.1 BTUs per pound of return enthalpy. On our supply side, again, we just extend that wet bulb line up diagonally to the upper left, and we arrive at 20.3 BTUs per pound of supply enthalpy. So how much enthalpy did this system remove? What's our difference? That's the difference between these two lines. And we arrive at 7.8 BTUs per pound. Our total heat formula takes on the same structure as our sensible heat and latent heat formulas. We're looking for our total heat, which is QT in this example, and we need our enthalpy difference this time. So here's the formula. Total heat equals enthalpy difference times CFM times 4.5. And just like the other formulas, that 4.5 is a new constant that will always be used. So the sensible heat formula had a constant that was 1.08. The latent heat formula had a constant that was 0.68. The total heat formula has a constant that is 4.5. So we see a very similar structure in that formula. We need a difference of heat times CFM times a constant. Let's use this total heat formula to determine what our total cooling removed from our sample air conditioning problem is. Now, if you recall, in our example, when we added our sensible latent heat, we arrived at 42,240 BTUs per pound of total heat. Now let's see if we come close to that same number by using the total heat formula. So again, total heat equals our enthalpy difference times CFM times 4.5. When we plug that in to how we plotted it on the chart, we get 7.8 of the enthalpy difference times 1200 times 4.5. So our total is 42,120. Very, very close to the previous number that we got by adding sensible latent heat together. So as you can see, you can use either formula to get total heat. It's whichever is easiest for you using the instrumentation and the methods that you have available for you at that time. Let's take a moment to summarize some of our formulas, and this is a good time to be writing these down. Our sensible heat formula is temperature difference times CFM times 1.08. Latent heat is grains difference times CFM times 0.68. Our total heat can be calculated by adding sensible plus latent, or we can use the total heat formula, enthalpy difference times CFM times 4.5. Our typical enthalpy difference in comfort cooling, this is another good piece of information to take down, is between 5.5 and 8.0 BTUs per pound. Our sensible heat ratio is determined by dividing sensible by total heat. And a typical sensible heat ratio should be between 0.7 and 0.8. So when can we use the total heat formula in the field? It's actually very useful for determining the actual capacity of a running air conditioning system. But for it to work, our readings have to be as accurate as possible. So it's highly recommended that you use smart probes. Most of the smart probe apps will calculate total heat or enthalpy for you, so you don't have to use these actual formulas. It's important to know them and know how your app is calculating them, but it's not something that you're going to have to take out a calculator and calculate every time. So how do we take these measurements of dry bulb and wet bulb temperature? How do we read CFMs? Well, as we mentioned before, in order to measure enthalpy and dry bulb and wet bulb temperature, we need a digital hygrometer that's able to read both dry bulb and wet bulb accurately. To read airflow, we'll need either a pitot tube, a hot wire anemometer, a flow hood, or a digital manometer. Now, a digital manometer may be the only thing you have on the truck on a day-to-day basis in order to read airflow. So if you're going to use that, we need to be as accurate as possible and accept the fact that we may not be able to take an extremely accurate reading, and we kind of have to factor that in our diagnosis. Now let's work our sample air conditioning problem using one of these apps. In this case, we're going to use the Fieldpiece app, but your other brands of hygrometers and instrumentation have their own apps. UEI has their own. Fieldpiece, of course, has a very good one. Testo has a very good app, and the MeasureQuick app can take all of these instrumentation and use them together to make some very good calculations and diagnosis of a system. So a lot of it just depends on what your preference is. In this case, we're going to use the Fieldpiece app because it very clearly shows the information that we're trying to get. So again, our cooling example, our AC unit that we've been already discussing, our return air readings are shown here, and our supply air readings are shown here. And when we calculate our airflow, we can enter that here in the airflow box. And when we put all that information into the app, it gives us our capacity of 42,120 BTUs per hour. So really the only thing that we are entering in is our airflow. Everything else is either being measured or calculated using the app and the probes. Let's talk about measuring CFM using static pressure. This may not be the most accurate method of measuring our airflow using external static pressure, but it could be the quickest, and it gets us close as long as we take good readings using tools that are readily found in a technician's toolbox. We can't use external static pressure if our blower wheel or evaporator coil are dirty. So the very first thing we need to do before we start trying to calculate total heat is to make sure that these are as clean as possible, as close to their brand new condition as possible. If they are not, then really we need to start by cleaning these devices. The manufacturer's blower data must be available for that specific model. So it either needs to be in the installation manual that's there on site, or you may have to pull it up online. Be very careful about drilling test ports. If you drill a test port and you don't know what's behind it, you could cause damage to the system. Test ports should be located in a straight line duct as often as possible. Supply static pressure has to be between the furnace and the case coil. So even though it may be easier to drill a test port after the case coil in this case, the case coil has a pressure drop on it, and that's not going to give you an accurate reading. You have to drill that test port between the furnace and the case coil, and of course be very careful in doing so. So now let's demonstrate how to calculate CFM using external static pressure. In this case, we have an air handler, a gas furnace that is a 42060 V17. This is an actual furnace that's made by Bryant. And this is their blower data from their installation manual. You can either find this manual by the unit if the installer's left it, or you'll have to pull it up online if it's not available on site. With a variable speed blower, there are 3 dip switches for this particular model that set the blower speed. We have to know where those dip switches are set so we know which line of the chart to use. So as you can see, we've got our unit size 42060 V17. We've determined where our dip switches are set, and we have an entire line of CFM values that we'll have to select from. So the next step is to determine what our external static pressure is and line that column up with that row. So our external static pressure that we measure, which is adding our return static pressure and our supply static pressure together, is 0.5 inches of water column. So what's our CFM? It's 1,190 CFM according to this chart. What if we're using an air handler with an X13 blower? Well, X13s are calculated in a slightly different way, so it's important for us to know how to do that. Our sample unit here is an FB4C036, and it's set on speed tab 3. So out of this entire chart, we've narrowed this chart down to just that one air handler and speed tab 3, so just one row of values. And with our external static pressure being at 0.5, that's what we measured. For speed tab 3, we arrive at 1,105 CFM. What if we have an old school permanent split capacitor blower, something that has been in furnaces and air handlers for many years until recently when we start seeing more variable speed and X13 motors? Well, we'll use this air handler. It's a furnace. It's a 0701408A. And here's the blower data for that furnace. Our blower speed currently is set to high speed. So out of that entire chart, again, we've just narrowed it down to the one model of furnace and the one fan speed of high. So we've narrowed this down to one row on this entire chart. And again, we've measured our external static pressure at 0.5. So what is our CFM? It's 900 CFM. So very similar ways of measuring CFMs using the external static pressure. If you have different kinds of blowers, you just need to know how to use those charts. When you take your external static pressure, you compare that on the blower data, you can get pretty close on what your airflow is, and you can plug that airflow into your formula. So now that we know how to take the measurements of wet bulb, dry bulb temperature, determining what our enthalpy is, determining what our CFMs are, how can we use this knowledge to troubleshoot systems in the field? This is really the point of this entire training module. We're going to determine the actual running capacity and performance of the equipment. We can compare that nameplate capacity or the manufacturer's cooling data against what we're seeing it actually do in the field. And we can quickly determine if airflow or refrigerant is a cause of poor performance, which is a very important piece of information when you're troubleshooting a system. We can quantify the performance improvement after we've made adjustments or repairs. And what's very interesting is that this is a non-invasive test. It doesn't require you to put refrigerant gauges on the system and potentially lose some of the charge or cross-contaminate it with a different system. So let's work a sample service call. On this call, our customer is complaining that their AC can't keep up in the summer. Let's see what we do know. Through the model number, we see it's a 3.5 ton AC. Our customer is complaining that it can't maintain temperature or humidity in the summer. And by visual inspection, we've determined that the filters, the blowers, and the coils are clean. So those cannot be a cause of the problem. The next thing to do is to hook up some instrumentation. Our supply and return hygrometers are hooked up. They give us these readings on the app. When we measure our CFM through static pressure, we arrive at 1200 CFM of airflow. Our app tells us that our system is operating at 42,120 BTUs per hour. So here's what we determine. This is a 3.5 ton unit and it's performing well. It's performing at 3.5 tons or 42,000 BTUs. Our airflow is okay. When we take an airflow per ton or CFM per ton reading, we're around 350 CFMs per ton. So that's not a problem. So the problem is not in the equipment. There's nothing wrong with how this equipment is operating. It has to be external to the equipment. So what will we recommend? Well, we may want to look into the air distribution. Is the right amount of air getting to the right places to provide adequate comfort? Could we have envelope problems? Is our house leaky or under-insulated that's allowing too much heat to enter into the home? And that could cause our unit to be undersized. So this gives us a direction in which to go. We know the problem is not in the equipment. We can start looking externally to the equipment and determining why there is so much heat being put on this AC system and it can't keep up. Let's work another service call here and see what this system is doing. The customer is complaining that the humidity is too high in the summertime. So when we get there, we verify a few things. We see that it is a 2-ton heat pump. It's very humid in the home. We verified that. We've also, through a visual inspection, to verify that the filters, the blower, and the coils are all clean, and they're not the cause of this service call. We also notice that the unit short cycles. It turns on for a few minutes, and then shortly thereafter it turns off. That's kind of a cause of concern for us. So we hook up our instrumentation, we start taking some readings, and this is what we get. What do we determine from these readings? Well, we see that this 2-ton unit is performing fair at 19,522 BTUs of enthalpy. Normally a 2-ton unit would be operating close to 24,000 BTUs. We're operating at 19.5. It's close. It's not a true cause of concern yet. But we also notice that our enthalpy difference is very low. When we subtract 22.9 from 26.3, we only get 3.4 BTUs per pound. Remember, we're looking for at least 5.5 BTUs per pound. So that's very low. And our temperature difference between supply and return, this is our dry bulb temperature split, is very low at 12 degrees. We also notice that our CFM is way too high. Notice when we measure our CFM, we calculate that, put it into our app, we're coming up with 1,276 CFM. For a 2-ton system, that's very high. That's over 630 CFM per ton. So when we look at our blower chart, what do we find? Well, our speed tap is currently on speed tap 5. Maybe we can change that speed tap to speed tap 1 instead and bring our airflow down. So here were our measurements before we made the adjustment. And here's what we have afterwards. Notice the differences. Our airflow was decreased. We changed our speed tap from speed tap 5 to speed tap 1, so we drastically reduced the speed of that fan. But look what effect it had. Before we had 19,500 total heat, now we have over 29,000 total heat. So our total heat and our performance actually got better by slowing the fan down. This may not make a lot of sense, but sometimes if you are running too high of a blower speed, your airflow is not spending enough time in contact with the evaporator for it to do any good. There's no heat transfer. By slowing that fan speed down, now we allow more dwell time across the evaporator, and it's able to absorb heat, and the result is better performance. Look what happened to our enthalpy before and after. Our enthalpy difference got better, and so did our temperature drop. All of that is starting to look normal. All these results came after simply slowing the blower down. So it's important to really take a hard look at airflow, because airflow has a drastic effect on total heat and system performance. So what are some uses for checking enthalpy and total heat? Well, as we've just done, we can troubleshoot comfort and performance problems without having to gauge up first. Putting a set of gauges on a system should not be your very first check. You should start with a non-invasive check, and only if that non-invasive check fails, then you can move to gauging up in other troubleshooting methods. You can also use this enthalpy and total heat checkups for quick performance checks of a system that's already been set up and commissioned, like during preventative maintenance calls. Now, you don't want to simply use an enthalpy and total heat check when you're starting up a system that's just been installed for the first time. Nor would you probably want to do it after making a major repair like a compressor replacement or having to remove the charge out of the system and put it back. Those are appropriate times to gauge up. But it may not be necessary to gauge up on every preventive maintenance call. Sometimes you can do a quick check of your enthalpy drop and your total heat, and you can determine that a system is performing correctly, and there is no need or no history that's going to require you to gauge up and look any further. A couple things to note though. If you're in a moderate humidity climate, you'll read lower enthalpy numbers on that scale between 5.5 and 8.0 enthalpy drop. You'll read it on the lower side of that scale, closer to 5.5. That's because there's not a lot of humidity in the air. But as humidity in the return increases, enthalpy will increase because there's more heat to remove. So for example, here in North Carolina, in the springtime, there's not a lot of humidity in the air. So our enthalpy drop will be a little bit on the lower side of that scale. But that same exact unit, come June, July, and August, when the humidity levels are a lot higher, will read a higher enthalpy drop because there is more humidity in the air and there is more heat for the evaporator to remove. But the temperature difference, the dry bulb temperature difference, should stay fairly consistent regardless of the return humidity. So typical supply return temperature drop is between 17 and 25 degrees. The system should be able to do that regardless of humidity. So when you combine those two checks together, you can have a pretty good idea about how a system is performing. So in summary, total heat is very useful in the field for quickly assessing how a system is performing. We can also troubleshoot and verify results. And all of these are non-invasive tests without having to hook up gauges to a system. Our sensible heat checks take into consideration the dry bulb temperature, but they don't take into consideration the moisture in the air. Typically, a comfort cooling system will remove 70% to 80% of the total heat of the system with sensible heat removal. And here's our sensible heat formula. Temperature difference times CFM times 1.08. Our latent heat checks take into consideration the heat and the moisture of the air. Typically, a comfort cooling system removes 20 to 30% latent heat compared to the total heat of the system being removed. And here's our latent heat formula. Our grains of difference times CFM times 0.68. And enthalpy. Simply put, enthalpy is heat. It's the total heat in the air. Typical enthalpy difference should be between 5.5 and 8 BTUs per pound on a typical performance check. Again, if the return humidity is on the lower side, then you'll see a lower number, closer to 5.5. If it's very humid in the space, then you'll read 8 BTUs per pound, or possibly even more, because there's more heat to remove. To calculate total heat, we can simply add sensible plus latent heat, or we can use the total heat formula, enthalpy difference times CFM times 4.5. So in this training module, I hope you understand that measuring total heat and enthalpy is very useful, very important to use in the field. It can be done non-invasively, and it can give you a very good idea about how a system is performing. Thank you for watching.